Okay, so we're going to take a look at electrostatics, charged particles and their interactions. I've got a problem that we're going to take a look at where it's the force between a couple different charges, but we're going to look at the force on just one of the charges. So I've got particles that are spread out from one another. My numbers include -5 microcoulomb over here at a position of -10 centimeters. I've also got way over here at +8 centimeters, strangely enough, a +8 microcoulomb charge. And I've got one other particle kind of in between, but not exactly in between, -5 microcoulomb, again, similar charges, at x equals 2 centimeters. And what I'm interested to know is what is the total electric force on this particle. The first thing that I want to mention, these are microcoulomb, once again, micro. Micro is 10 to the -6th. They are 1/1,000,000th of a coulomb, or in this case, 5/1,000,000ths of a coulomb. All right, these are all in a straight line, even though I may not have drawn them properly that way, but we'll treat them as all in a straight line. And this is how they're related to one another. All right. If we want to find the total force acting on this particle, in fact, it might help if I name these. So I'm going to call this one Q1. I'm going to call this Q2. And I'm going to call this Q3. You can name them whatever you want. You could use A, B, and C. You could use Larry, Moe, and Curly, whatever you'd like. But the key thing is, and this is why I've chosen this one to be charge 1, I want to know the force on charge 1. It doesn't have to be charge 1, it could be anything, but making it number 1 keeps my focus on it. Now the problem is, this charge has a force on it from this charge and another force on it from this charge. We have a complex problem. How do we deal with complex problems? Well, with superposition. That's a fancy term, but basically what it means is superposition is where you take a complex problem, you break it down into smaller parts, you solve those parts, and then you take the solutions of those and add them together. Many things in the real world are subject to what we call superposition, which means we can solve them this way. Now, we're going to have to add them appropriately, but we'll see more on that here in just a little bit. So what I'd like to do is I'd like to find the force in between these two particles, which I could call force, the electric force between 1 and 2. So I could call that Fe12. Or the electric force of particle 2 on particle 1. Over here, I'm going to be looking for the electric force between 1 and 3. All right, well, we have an equation for finding the electric force or the electrostatic force. They both mean pretty much the same thing. It is Coulomb's law. Coulomb's constant times the charge times the other charge divided by the distance between them squared. All right, well, if I'm going to start off, I would go through and I would find the electric force between 1 and 2. That's going to be K, which my numbers warn me that we are actually using 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. In class, we usually use 9.0, but this is programmed with the more precise 8.99, so that's what we're actually going to use, just so we can maximize our ability to get the correct answer. All right? We're going to need the charges. We need -5 times 10 to the -6th coulombs. We were given -5 microcoulombs, but microcoulomb is not the SI unit, just like gram is not the SI unit. Instead of gram, we use kilograms, and instead of microcoulomb, even though that's what we've been given, the SI unit is the coulomb. So I need to convert these to coulomb. Well, both of them are actually -5 times 10 to the -6th coulombs. So I'll write those in. Great, we've got the two charges that we're looking at, Q1 and Q2. I'm going to divide this by the distance between, distance between them squared. This is at negative 10, so we have to go 10 centimeters over to get to the origin, 0. Then we have to go over 2 more centimeters, which means the distance is 12 centimeters. But as we just talked about, centimeters are not the SI unit. We want to put SI in. So 12 centimeters is 0.12 meters. That's the distance between them, and I'm going to square that. Okay? I go through, now that I've got all my numbers, I can start calculating this up, and we find that the electric force between 1 and 2, we're going to find it's the same force on each of them, though they point in different directions. I've actually solved this a little bit before. When you run these numbers, you should end up with 15.6 newtons, or something very close to that. All right. Now, 15.6 newtons, that's our magnitude, the value of it. We want to find out which direction it's in. That's an important part of forces. So, if I'm looking at these two, this one will feel a force pushed off to the left because they're going to try and repel one another. This one will feel a force off to the right, and since I'm looking at the forces on Q1, I know that this is a 15.6 Newton force to the right. Okay, let's take a look at the next one. And by next one, I mean the next part of this problem. This is all still one problem. We need the force between charges 1 and 3, so that I can take the force on charge 1 from 2 and the force on charge 1 from 3, and I'm going to add them together in keeping with superposition. Okay, well, we know that Coulomb's constant is 8.99 times 10 to the 9th times charge 1 was negative 5 times 10 to the negative 6th Coulomb times the other charge, Q3, which is positive 8 times 10 to the negative 6th Coulomb, 8 microcoulomb. Specifically, 8 positive, or positive 8. I need the distance between them. Well, this is at 2 centimeters, and this is at 8 centimeters, so it means that they are 4 centimeters apart. 0.04 quantity squared. I'm sorry, not 4 centimeters. I'm bad at math. 2 and 8, 6 centimeters. I was thinking of something different. Helps if I stay focused, but math errors can happen to anyone. When you go through and you solve this, you should end up with, if you're using the right numbers, about, nope, not that, 99.9 newtons. Except, you're going to have a negative, because I have negative here and a positive. Those two negatives don't cancel out. Numerically, we end up with 99.9. The negative tells us that these two are attracting. It does not actually tell me my direction. The force is not necessarily in the negative direction. All this negative tells me is that they attract. So I need to go back and I need to look at this. If they attract, then the force on this negative charge here, the one I care about, it's going to be pulled to the right. This negative charge is going to push this one to the right, and this positive charge will pull that one to the right. So they are actually, despite the fact that one was positive and one is negative in our equation, they actually work together. So, writing this out, we actually have positive 99.9 newtons to the right. Both forces are to the right. Do not get tripped up on the positives and negatives of this. They only tell you if the particles are attracting or repelling. All right, now we need to finish this up to find the total force on particle 1. We're going to add the force from charge 2 on charge 1. I'm going to put vector signs on these. This is what I talked about before. When we add these solutions, we add them appropriately. These are vectors, so they must be added as vectors. Well, on the upside, this one is to the right, and the other one was also to the right, so they are both positive numbers. Positive, right being our positive x direction. So this is going to be positive 15.6 newtons plus a positive because it's pointed to the right, at least for the force on charge 1, and that is 99.9 newtons. That means that I end up with a total force of 115.5 newtons to the right. Or, writing it in the proper vector notation, though that's not required here, 115.5 newtons at 0 degrees. It points straight to the right. Both of these work together. This negative charge is going to push this negative charge to the right, and this positive charge will pull this negative charge to the right, so they both add together. Oh, and that is actually the value we're supposed to get.